this is Calculus 12, Chapter 3.1. We're going to be looking at the derivative of a function. For Chapter 3, we're going to be looking at lots of derivatives. There are real-life applications to derivatives, but really we need to learn how to do derivatives so that we can do integration. Integration is the more complicated problem in mathematics, and it's actually more needed in real-life applications. Okay, so we've already looked at the derivative at a point A. So we have the slope equals limit h is approaching 0, f of a plus h minus f of a all over h. And let's consider derivatives as a function. So we have f prime of x equals limit h approaches 0, f of x plus h minus f of x over h. So all we're doing is substituting this function notation, and we have an x instead of an a. It's not a big differentiation, but we're thinking of it as a function. So rather than calculating at a point, we can calculate it at any point. If this limit exists for every x in the domain, then we say f is a differentiable function. There's a second definition, a derivative at a point. F prime of a. Okay, we have limit x approaches a, f of x minus f of a, x minus a. Okay, and this method relies on being able to factor x minus a from the numerator. That way we can cancel out with x minus a in the denominator. So let's look at an example. We'll just do x squared because that's a simple example. Limit h approaches 0, f of x plus h minus f of x over h. We substitute. Limit h approaches 0, x plus h squared minus x squared over h. So we're substituting. Now we need to expand. Limit h approaches 0, x squared plus 2xh plus h squared minus x squared over h. Now we can cancel. We're going to cancel x squared first, and then we can cancel out an h second. Okay, you can't cancel these first because we need an h in every term. Once we've canceled out the x squared, now we have an h in every term, and we can cancel out h's. Now we just need to break it up into separate terms. We have 2x plus limit h approaches 0, h. That's 2x plus 0. So that's just 2x. Okay, let's look at the second way of doing this. F of a equals limit x approaches a, f of x minus f of a over x minus a. Limit x approaches a, x squared minus a squared over x minus a. This is a difference of squares. So we have x minus a, x plus a, x minus a, and we can cancel out the x minus a's. Now we can break up our limits. X plus limit x approaches a of a. So we have a plus a, and that equals 2a. Okay, it's the same thing. We can use this as a function as well if we wanted to. But by convention, f prime of x is for a whole function, f prime of a is actually just for a specific value. But again, we can use this as a function if we wanted to. It's just not convention. Okay, rationale. We only need to find the derivative of a function, and then we can calculate the slope anywhere. And here's the two ways of viewing those derivatives. This is the first one, and this is the second one. So we have f of a plus h minus f of a over h, f of x minus f of a over x minus a. And we have one-sided limits. So you can take the limit from the right or from the left. There's two ways to view taking the limit from the left. We can have h approaching 0 from the left, or we can have h approaching 0 from the right. So this is the way the book does it. You might want to do this for a better understanding. Okay, so if we look at this point, A, we're taking h greater than 0, so we're adding h. So this is the derivative on the right. Here we're doing b. We're doing b plus h, but h is negative, so we're actually going to the left. Okay, if we do it this way, we have b, we have h here, h is greater than 0, and we're subtracting h. So some people find this easier to understand. So we're going to put down the note, same, but easier to understand because h is positive. Okay, so for some people this is easier to understand. For some people, they prefer this. Okay, let's look at some notation. This is Lagrange's notation. This is Leibniz notation. And we use both of these. However, this is preferred. For chain rule and integration. We'll get to integration later. And to complete your understanding, this is Euler, which is not used very often. This is Newton's, and this is used in physics. And here's just a graph of x squared and the derivative 2x. And this will help us understand how we do a derivative from a graph. Note that the derivative is negative. Here we're coming downwards. Anytime we're going downwards, the derivative is negative. Anytime we're going upwards, the derivative is positive. And anytime we have a minimum or a maximum, the derivative is 0. So it's 0 there. So let's take a look at this graph and plot the derivative. And here are the notes. Look for a horizontal tangent of f of x and plot along the x-axis because the derivative is 0. Plot holes at sharp corners and cusps of f of x. Determine the slope of the lines of f of x and plot them horizontally. Slopes of parabolas are drawn as lines. Okay, so if we look up here, this is a parabola. The derivative is a line. Okay, using the rules, let's start off. So this is a line, so the slope is going to be a horizontal line. That's what number 3 says. Okay, so we're not given a scale here, so we can treat this as a unit graph. This is going up by 1. So right now I'm just going to put holes at the endpoints. This is a line. The slope is 0. So we put holes here, and we draw a line there. Okay, this looks like a parabola. It could be a tangent function. But anyways, we're constantly going up. So the derivative is positive. So put a hole there. If it was a parabola, then this is going to be a straight line. If it's a tangent, then it's going to curve. Okay, this has a slope of -1. Here we're increasing, but we have a maximum here. A maximum, the slope is always going to be 0. So the derivative is going to be 0. This is increasing. So the slope is positive, but the slope is getting smaller and smaller. So we're coming downwards. And if you look at this, we can also say it's a parabola. So I'm going to put a hole there, and we're going to come down. This is decreasing, and the slope is getting more and more negative. So we can just treat it as a line and go like that. Okay, there's an arrow here, so we should end up with an arrow there. Okay, so this, and this. These are technicalities. Leave open if unsure. Okay, so here, there's a limit on the left, there's a limit on the right, they don't match. So this is definitely a hole. Same thing here. We have a limit on the left, we have a limit on the right. They don't match, so these are definitely holes. Here we have a jump, it's also called a cusp, hole, hole. These are endpoints. So we can do one-sided limits. So we can actually fill this one in, we can fill this one in, because the limit exists. Same thing here. This is a line, the derivative exists. Here we have to decide, is this a tangent function where it's a vertical asymptote here, or is this a parabola where it would continue through this point? If you're sure that this is a parabola, we can fill this in. If you're not sure, leave it open. And for our tests, I won't take off any marks if you leave these open. But if you're taking calculus at university, ask your prof whether they want you to fill this in or not. And lastly, I'm going to give you the derivative of a power. We say d dx, x to the power of n, equals n, x to the power of n minus 1. So, for example, if you had x to the power of 5, this is 5, so we put a 5 here. We have x, we take 1 away from 5, so that's 4. So this is the derivative, d dx, derivative of x to the power of 5. And you might want to note that this is Leibniz notation. And that completes this lesson.